All right, well, welcome back everyone to our last grad student seminar of the semester. Today we have Dylan Galt, and he'll be talking about well-rounded retracts.
Hi, thank you for having me. So this is my first time speaking at the seminar here, which is very exciting. What I'd like to do today is I'd like to talk about probably 3/4 of the time about something called the well-rounded retract, and then hopefully if there's time at the end, get to something called the well-tempered retract. All right, so what are the objects we're going to be working with? First, let me just say that this talk is very much indebted to Mark McConnell, and here I'll list at the end some of the papers that that you can look at for some of the information in this talk, but in particular, there will be some pictures and animations which I'll mention that were created by Mark McConnell. So do acknowledgement there when we get to those. Okay, so the setup can be done a little bit more generally than this, but for this talk, we're going to fix the following objects. So we have GLN over the reals. We have its maximal compact subgroup, O of n. So these are the orthogonal matrices, and in particular, these preserve the standard Euclidean inner product on Rn. We have an arithmetic subgroup, or possibly several different arithmetic subgroups as the occasion might arise. So just to fix ideas, what you should think is that this is something like SLNZ or GLNZ. So this is somehow the integer points on the algebraic group that we're looking at. And we have the space of homotheides. So the homotheides, these are just the matrices. Let's see. So these are just the diagonal matrices with some non-zero real scalar along the diagonal. Okay. So in particular, these scale the matrices in GLN, and so we can normalize everything to have determinant 1. And this will be useful, as we'll see. Okay, so what do we get with this setup? Well, the main object that we want to understand is this Riemannian symmetric space. So what you do is you look at this Lie group. So in our case, this is just SLNR. And we've normalized everything to have determinant 1. And you quotient out by the maximal compact subgroup K. In the literature, you'll see that there's either a left action or a right action. It depends on what you want to fix. In this case, the maximal compact subgroup will be acting on the left, and the arithmetic subgroup will be acting on the right. Okay, so what is this? Okay, so it's a symmetric space in the sense that every neighborhood has a neighborhood, every point has a neighborhood, and all of these neighborhoods look exactly like each other under the action of the Lie group. And what is particularly interesting about this? Okay, well, one thing is that this is non-compact, and it has it gives rise to essentially a manifold, not quite. It has finite stabilizers of some points. So it gives you a non-compact orbifold when you mod out by the arithmetic subgroup gamma. And both of these things are non-compact. So one thing that we could talk about in this talk, but we won't, is various different compactifications like the Borel-Serre compactification. So there are really interesting ways of trying to compactify this space X such that when you mod out by gamma, interesting things happen. And the point is that from the perspective of this talk, the point is that somehow X is a contractible manifold, so its topology is not quite as interesting as X mod gamma. And X mod gamma, the topology gets quite wild. So the goal is to understand the topology of X mod gamma via a subspace of X mod gamma, which is much easier to understand, but captures sort of all the cohomological information of X mod gamma. So we're going to build something W mod gamma, which sits inside X mod gamma, which is a sort of a much more combinatorial object and which captures the cohomology of X mod gamma. So this is the goal. Okay.
Dylan.
Yeah.
As a reminder, is K the ON?
K is ON, yeah, K is ON.
And then H, what is this again?
H, these are the homotheties. So this
Oh,
is
okay, I
really
see.
just,
Right.
yeah, this is really just, for us, this is really just this space. Yeah. Okay, so the idea is to actually think about, this is somehow a really beautiful insight, I think, is to think about the symmetric space in terms of lattices. So this is going to be the theme of the talk, so let's understand how that does. So what we're going to do is actually build something called the well-rounded retract, which is due to Ash in 1984, and which generalizes a lot of classical pictures, which we'll see after we set some notation. Okay, so a lattice is a finitely generated subgroup that contains a Q basis for Rn. So this is something, it's not necessarily an integer lattice. It could be something that looks like this. And then an integer lattice, this is sort of the more standard thing. This is something which looks like this, where we have points that are equally spaced in the plane at 1 apart, or maybe we have double that, so we have points that are equally spaced in the plane at 2 apart. So these are our integer lattices. Okay, and so we're now going to fix an integer lattice L0. All right, and work with that. So this is going to have some kind of stabilizer via a left action. So think of, if this is sort of the running example to think of. So if you fix the square integer lattice, which is just the square lattice that I drew, that's just this lattice, say in the plane, then A here is going to be just the integers, and it's also going to have an arithmetic subgroup of the algebraic group that we fix. So in this case, the general linear group that fixes this lattice under left multiplication. And in our case, that's going to be all of GLNZ if you just fix the standard square lattice. All right, and so now we want to define a space of lattices, Y, which are stable under the action of A, and such that every lattice in Y is isomorphic to our fixed lattice as an A module, so as a Z module. So in particular for this example, this is just a space of integer lattices in Euclidean space, which are identified up to homothety. So the two lattices I drew earlier where one, every point is linked one, these are identified. And they're all isomorphic as Z modules to the standard square lattice. So, okay, so what are different elements of Y? Well, different elements differ by rotation, for instance. This is one way they could be different. So if you had a lattice which is sort of off at an angle like this, so you've rotated by pi over 4, these are different. They're not identified up to homothety. Okay, but when we quotient by gamma, these will actually be the same. Okay, so in two-dimensional space, the space mod gamma is actually quite small, as we'll see. All right. Sorry, if we quotient by k, they'll be the same. Right. So right now we're just working, this is just a lattice in Euclidean space. Okay, and now we want to understand how we can describe this in terms of the algebraic group. So I'm going to claim that there's actually an identification between the space of lattices mod homothety that are isomorphic to our fixed lattice and this quotient space, where we quotient out by both the homotheties and we quotient out by this stabilizer. So what is an element in this space? Well, an element in this space looks like this coset, G gamma naught, where you think of G is something in GLN mod homothety. So G is something in SLN, right? And to this, we associate the translate lattice, where we have the translate of our fixed lattice L naught. So this is isomorphic. This is a lattice L, which is isomorphic to L naught by the action of this point G. And similarly, we can go back. So we can actually begin to build our quotient space, our Riemannian symmetric space, as a space of lattices. Okay, but we now need to understand how the maximal compact subgroup acts. And the maximal compact subgroup preserves the Euclidean inner product on Rn. So these are rigid motions that act on our lattices. Okay, and so this together gives us this identification, where you recall that X is HK mod G, or G mod HK. Okay, so this is the key sort of starting point where you understand the quotient of your symmetric space mod gamma as the quotient of a space of lattices by the maximal compact subgroup. Okay, and I'll do one more thing which sort of reinterprets this. So this is one more definition of what a lattice is. I think this takes a little bit of time to kind of get used to as a definition, at least it did for me. It's not exactly clear. I think it's quite subtle why this is useful as a definition, but hopefully later on we'll see I can explain why this is useful. So a marked lattice is a function which describes the manner in which we are transforming our fixed lattice to get a new lattice in Rn. Okay, so it's a function that associates to an element of GLN the translate of the lattice. Okay, so marked lattices are just, marked lattices mod homothety are just this quotient space, because for every G, we give rise to a new marked lattice GL naught. Okay, and we're identifying them modulo homothety. And so now, and moreover, what we see is that our whole space of lattices Y can be identified with marked lattices mod the action of gamma naught. Okay, and now this is how marked lattices are actually quite useful. So what you see is that maybe I can draw a diagram which makes this slightly easier to visualize. Yeah, I'll draw this. Yeah, I'll draw this in the corner here. But the point is that an element in X in our symmetric space. So this is a coset in this quotient. An element here, this coset representative G gives rise to a marked lattice. And so the space of marked lattices descends to the symmetric space via the quotient by K, in a similar manner to how the space of lattices descended by the quotient to X, where you quotient by gamma naught. So the diagram is you have marked lattices, which go to the space of lattices here, which goes down to the quotient by gamma naught. And on the other hand, you can go here by quotienting out by K, and you get to the homogeneous space, and then you get, so this is the quotient by K side, and this other side is the quotient by gamma naught side. So depending on whichever perspective is more useful for you, you can look at this either way. Okay, if this is not entirely clear, that's okay. We'll come back to, these definitions will come up again. But the point is that the point somehow is, the most important thing right now is this correspondence here, where you can view X mod gamma naught, where gamma naught is the stabilizer of your fixed lattice L naught, which is sort of fixed forever. You can view this as a space of lattices on which the maximal compact subgroup acts, or you can view this as a space of marked lattices on which gamma naught acts, and on which the maximal compact subgroup then subsequently acts via the quotient. Okay. All right, so now we're going to build a well-rounded retract. So here is something that, what did we gain by doing this? Well, one thing that we gained is that reinterpreting things in terms of lattices, we can now specify some kind of arithmetic information about the lattices. And we'll see this come up later on in the talk as well. So we've gained a little bit of information in reinterpreting the symmetric space in this way. So in particular, if you fix, so remember why these are the marked lattices now. So if you fix a homothety representative inside this class of marked lattices, so this is just H mod G. So you fix a homothety representative, it gives you a corresponding lattice just some translate of L naught. And you define the minimal vectors of this lattice to be the set of vectors in the lattice for which the norm is minimal among all those that are non-zero. Okay, so for instance, if I have the standard lattice like this, these vectors are minimal. Okay, all right. So there will be more than one. There will be more than one in general. And you define this lattice to be well-rounded if the span of these minimal vectors, the R span, is the whole vector space. So for instance, in this case, for the standard lattice in Z2, it's clear that this is well-rounded because the two minimal vectors span all of R2. Okay. All right. So the well-rounded retract, W, is defined to be the set of well-rounded elements in X. So remember X, this is HK, G mod HK, and we have our marked lattices, H mod G. So these are so inside, and you go from here to here by quotienting out by K. So inside X, you have a K coset of representative, which is represented by some marked lattice. And if that marked lattice is well-rounded, then this gives you an element inside this space. And if you, gamma naught was the stabilizer of our fixed lattice L naught, and given any arithmetic subgroup inside gamma, we define the well-rounded retract inside X mod gamma to be the quotient mod gamma. And remember, we have an action of gamma naught on marked lattices, so this is well defined. That was sort of the point of the diamond diagram, where you could go either via K or you could go via gamma naught. So what can I say about this? Well, one thing of interest is that the well-rounded elements here are already interesting inside of the symmetric space. But even more interesting, you can quotient out by gamma and you have something which lies inside this space. And so the main theorem is that this actually computes the cohomology here. The other thing, which we'll come to in a second, the other thing of note is that when you, this is very important in my mind, when you build the well-rounded retract, you have to specify some data. So the key data that we specified is we fixed the lattice L naught. Okay, we also fixed an inner product. So our definition of well-rounded was with respect to the fixed Euclidean inner product. When we talk about well-tempered retracts, we'll see that you can actually generalize this by weighting this inner product, and you can build a family of these well-rounded retracts. So in order to specify the well-rounded retract, you have to have fixed the lattice and you have to have fixed some data about how to measure distance. Okay, so let's do pictures and an example. All right, so let me come back to that slide. Let me give this picture first. Okay, so this is the standard picture of the upper half plane. And inside the upper half plane, we have this tree. And this tree is made by, if you continue these circles, these are geodesics in the upper half plane, and these vertical lines are also geodesics. And the beautiful thing is that this tree is actually the well-rounded retract for this symmetric space. So this is SL2R mod SO2. This is the upper half plane. And the well-rounded retract in the upper half plane is this tree. Let me delete this. Here. So the well-rounded retract in the upper half plane is this tree. Now, how do you see this? So this fundamental domain we'll talk about in a second, but how do you see that it is this tree? Okay, so the key idea is to consider the following process. So fix the standard integer lattice and look at its stabilizer, gamma naught. Now, remember that Y is the space of lattices modulo homothety that are isomorphic to L naught as the Z module. So these are all integer lattices. So if you have any marked lattice, so your marked lattice F is going to be some G translate of L naught. So take the standard basis vectors for L naught. And we want to analyze now the marked lattice GL naught. So the point is that marked lattices differ often by some kind of rotation, but all the rotations are in K. And remember, X is formed by modding out by K. So you can identify your fixed marked lattice with one that has been changed by a rotation and that has been changed by a scaling action. So we can rotate the image of the first basis vector in L naught so that it lies on the x-axis, and we can scale it so that it has length 1. So if we come back to the picture, given our lattice, which might be something like this, we can rotate this first basis vector to be on the x-axis and have length 1. Then, by a reflection action, the second basis vector is going to be somewhere, and we can make it lie somewhere in the upper half plane. Okay, so this second basis vector, its image in the upper half plane, this gives you the identification between X, which is viewed as a space of lattices, with the upper half plane. Now, if you look modulo gamma equivalence, everything in the upper half plane is, everything in the upper half plane is inside this fundamental domain. So this is the whole shaded region here is the fundamental domain for SL2, and the region on the right half is the fundamental domain for GL2. Now, the point is that modulo gamma, we can put everything in the upper half plane into this fundamental domain. And then for GL2, the well-rounded retract modulo gamma naught is this arc right here. So this arc is this arc here, it's W mod gamma naught. And the fundamental domain for X GL2 or X mod gamma naught for GL2 is this whole crosshatched region here. And so lo and behold, there is a deformation retract of this crosshatched region down onto this arc. And perhaps more extraordinarily, it's not just any old deformation retract, it's actually gotten by doing a geodesic flow downwards along these vertical geodesics in the upper half plane. So this tree, which gives you the well-rounded retract in the upper half plane, its quotient modulo gamma gives you this arc onto which the symmetric space modulo gamma deformation retracts via a series of geodesic flows down these vertical line geodesics that are perpendicular to the x-axis in the upper half plane. Okay, so when we come to the theorem which says that W mod gamma computes the cohomology of X mod gamma, now you see a specific example of when that is true. So it has the right dimension, and there's actually a deformation retraction that's gamma naught equivariant, and it turns out it's a theorem due to Avner Ash and McConnell in a paper we'll discuss a little bit later, that this deformation retraction is gotten by a series of geodesic flows, which look sort of precisely like this in the upper half plane example. Okay, so let me just state the theorem, and then we'll pause for a second.
Could I ask a question about the picture?
Yeah.
Is the reason why the well-rounded retract is that arc because all those vectors are length 1?
Right. So, you mean, is there a reason why modulo gamma it's this part of the arc?
Right. Is it just because all those vectors have length 1, so they have the same length as the one on the x-axis that you fixed? So they're both like minimal length or something? Is that?
So I think it's kind of difficult to see why it is exactly this particular arc. What can I say about it? So I think the way to see it is that yeah. So what I would say is the way to see it is that is very similar to what you said. So basically you get the well-rounded retract via a process of picking first this basis vector, the first basis vector, which you rotate to get on in this direction, and you shorten to have length 1. And then the rest of the process is you look at the linear span, the real linear span of this basis vector, and then you pick an orthogonal direction. And then you shorten everything, you scale everything down in that orthogonal direction until it hits this tree. So the point is that when you shorten everything down in this orthogonal direction until it hits this tree, everything is going to lie somewhere on here. And then with respect to the GL2 action, these two sides of the arc are the same. Does that make sense?
Yeah, got it. Thank you.
Yeah.
Dylan, I think the way I see it, at least, that arc is the unique arc that lies on a unit circle. It has length 1, doesn't it? And then you don't consider the left part as well, because the left part and the right part is just identical to each other, doesn't it?
Right. That's right. Yeah. That's right. And I think the procedure to remember, which is often useful in reading about this, is this sort of repeated procedure of you fix one direction, you shorten everything until one of the vectors has length 1, and then you look at the linear span, and then you look at the complementary directions, and then you repeat this procedure. So it really is an iterated procedure where you of shortening things until something hits length 1. Yeah. Okay, so here is the theorem. So the theorem is that W mod gamma is, remember, so gamma is any arithmetic subgroup that you choose inside gamma naught. This is a cell complex, it's compact, and it has dimension, the virtual cohomological dimension of gamma. So what that means is that, you can compute this through gamma equivariant cohomology, or you can compute the group cohomology of gamma. And W mod gamma has this dimension. Okay, and it's a deformation retract of X mod gamma. So it has the cell structure, and its cell structure comes by, you look at the universal cover, and it actually descends via a certain barycentric subdivision. This is a little bit unclear how this process actually works from what I've just said here, but because this universal cover is actually not, it's ramified. But the point is that W mod gamma actually has a cell complex structure. So it really is I think one can think of as a combinatorial object. And the computational consequence of this is that if you want to compute the cohomology of X mod gamma, you now have a lower dimensional space which has a concrete construction which computes the cohomology for you. Now, there's still a lot to be done with this, but this goes a long way, at least for GLN and SLN. This goes a long way to helping understand the topology of this space. Okay, so now I want to take a little bit of a detour and discuss. So this everything here, this is basically coming from Avner Ash's, mathematician named Avner Ash, a paper that he wrote in 1984, which extended a lot of earlier results by other mathematicians, Soule and various others. But this theory really kind of started in many ways with early work in 1908 by Voronoi, a mathematician named Voronoi. And so I want to talk a little bit about the classical theory. So if you maybe want to phrase the problem of this aspect of this theory, the idea is to try to find some kind of gamma equivariant retract. So you want to find a spine inside your symmetric space, which is gamma equivariance. You can quotient out by gamma, and you get a regular cell complex, and it computes the cohomology of your symmetric space. Okay, and so Ash gives an answer in the case of SLNR, but there's a lot of really beautiful initial work going back to the early 20th century, and this is what that work looks like. So the starting space is this cone. Let me see, does this come up? Okay. So you look at the real vector space of real quadratic forms, and inside here, you have an open cone of positive definite quadratic forms. So when n is equal to 2, the dimension of this open cone is 3. And when you quotient out by homotheties, you get something that has dimension 2. And this is why you view this open cone becomes a disk when you quotient out by homotheties. So this is the Klein disk model. I mean, it has a different geometry, but this is we'll come to that in a second. So inside the space of quadratic forms, you have these positive definite quadratic forms, and they form an open cone. Why do they form an open cone? Well, the idea is that if you have on the boundary of this cone, you have a positive semi-definite form, and then you can scale this positive definite semi-definite form by homotheties, and you get all of these sort of lines along the boundary. So these are this thing really is a cone. By cone, what is meant is basically it means a convex hull, but you only take positive linear combinations. You don't allow things like if you take the convex hull in x and y, a and b have to be positive. This is what is meant by a cone. Okay, and so inside this cone, you can build a reduction theory. So you can build a similar kind of cellular decomposition as we ultimately want for sort of the Klein disk model. So it's a classical result that this open cone mod homotheties is SLNR mod SON. So that is what I was saying earlier about the fact that in the n equals 2 case, this has dimension 3, and so when you quotient by homotheties, you have dimension 2. So this is the sort of the identification with the disk. And the theorem of Voronoi, which really sort of starts everything, is that this open cone admits a locally finite decomposition into open cells, where each of these open cells is a polyhedral cone on points on the boundary. And the set of these polyhedral cones admits an action by GLNZ. So what does that look like? Well, it looks like the following. So let me just say again in pictures what I had just said. On the boundary, so this is your open cone. These are the positive definite quadratic forms. On the boundary, you have these semi-definite quadratic forms, and you take these sort of these positive convex hulls on these boundary points, and these give you these open cells which decompose the whole open cone into a union, into a locally finite. It's really a tiling. It really gives you a tiling of D+. Okay, so what is the usefulness of this? Well, the point is that, and now you'll start to see the connection with minimal vectors and lattices. The interesting thing from Voronoj's perspective, working with quadratic forms, is it turns out that, well, the question is, how do you prescribe these faces? So each of these is a face, calling this a face F. And D+, remember, this has a decomposition into this space of faces. And the question is, how do you get these F? And it turns out that they're prescribed by arithmetic information coming from your quadratic forms, which is quite extraordinary. So you get this geometric decomposition of D plus by looking at the arithmetic of these quadratic forms. And the geometric information comes as the arithmetic information comes as follows. So you call a positive definite quadratic form perfect if, I mean, roughly speaking, we have to be a little bit rough here. It means that it's completely determined by its minimal vectors. So the vectors on which it attains a minimum. So you have these perfect forms which are completely determined by their minimal vectors, and these correspond to faces inside the cone. So you take the cone on the minimal vectors, and you take its closure, and a face inside this closure. This gives you the faces f. These f phi are what give the decomposition of D plus. Okay. So, yeah, in the interest of time, maybe I will skip this. I will skip this slide. We can come back to it if there are questions. Okay, so now let's look at some pictures and some animations. So here are the two perspectives. So on the left we have the Voronoi perspective, and on the right we have the Ash perspective. To sort of be reductive about this. So what do I mean? Well, this is the upper half. So this is the case n equals 2. So remember we said dimension of D plus mod homosades is 2. And so this is a disk. And it's identified with SON mod SL2R. Sorry, SL2 mod SO2R. And so these are the Voronoi cones. So these are the faces that give the decomposition of this symmetric space into this locally finite union. On the other side, and you see now, which is sort of dual to this picture, is if I begin to sort of try to build a dual complex here to these cones, what I'm actually building when I do this is I'm building the well-rounded retract. So this is the well-rounded retract from the Klein disk perspective. So there's actually this, you can do this change of perspective depending on what you want to look at. You have the well-rounded retract, which you can understand as this one-dimensional tree, or you can look at the dual picture where you have these two-dimensional cones which give a decomposition into, this is a tiling perspective and this is sort of a graph tree perspective. Okay, and both of these are quite useful. Maybe I can say something quickly about that. There are some attempts to try to extend this to sort of nonlinear cases, and one attempt is successful attempt is by Mark McConnell and Robert MacPherson, where what they did was they were able to actually build a reduction theory sort of a la Voronoi for the symmetric space for SP4R. And what they were able to do was use Voronoi cones. They were able to construct certain cones which they could intersect with the symmetric space. And even though it's very nonlinear, they were able to prove that these intersections are nice enough that you get a similar kind of decomposition. So this perspective is actually quite useful in many cases. But, and this sort of, these pictures show how you go from one to the other. This perspective is what we'll just sort of finish talking about, because this one is quite useful when you want to compute cohomology. All right, so I have some, yeah, right. So the last, maybe I'll take 5 or 6 minutes if that's okay. The last few minutes, what I want to do is change perspectives a little bit and talk about this idea of the well-tempered retract. So the well-rounded retract is what we've been talking about. The well-tempered complex is this new complex due to Mark McConnell and Robert MacPherson. They have a paper on the archive, which was just published late last year, which I'll give a link to at the end. So what is the idea of the well-tempered complex? So the well-tempered complex is, remember, when you specify the well-rounded retract, you have to fix a lattice and you have to specify this Euclidean inner product, which measures whether or not something is well-rounded. The idea of the well-tempered retract is you pick a family of temperaments tau, which range in some interval. And for this family of temperaments tau, for each tau, you define a scaling factor for your Euclidean inner product, which remeasures what it means to be well-rounded. And then you build a complex, which is essentially a fiber bundle where every fiber is a different one of these well-rounded retracts. And what is the usefulness of this? Well, okay, so I think we perhaps will not have time to talk about Hecke operators, but the idea from this picture is that it turns out there are some really natural operators which operate on this picture here and have a lot of really interesting number theoretic properties. And what they do is that they change the cell complex structure here. So what McConnell and MacPherson did is they built a whole family of retracts which actually deform in a manner which is sort of consistent or related to the way that the Hecke operator acts. And so it turns out you can compute operators on the cohomology of these spaces by building this well-tempered retract, where at each fiber you have a different well-rounded retract, and the cell structure, you look at how the cell structure changes, and the manner in which it changes gives you information about how this Hecke operator acts. So maybe I can finish with some pictures. And at this point, I'm going to have to stop sharing my screen here. How do I do that? And start sharing my screen so I can share a GIF that I have. Okay, can everyone see this? Okay. So what does it look like? So this is something that Mark McConnell created. So let's look at what happens when you start to deform the complex structure. So if I play this, you get this following sequence where you see that there's no change, and then suddenly there's a change at what's called a critical temperament. So at each temperament, tau, you have a different cell complex, and you see this, the structure doesn't change, and then right here, it changes. And so this is a critical temperament. And so the study of these well-tempered complexes amounts to studying what happens when you go past these critical temperaments and what changes. So this is an example in which you have these two trivalent vertices which meet and change directions. There's another example here, which is where you have a different Hecke operator. So you build a different well-tempered complex. And in this instance, you'll see that actually now you have 3 sets of trivalent vertices that are meeting at a point. So the behavior can actually be quite complex. It turns out it's a theorem that there are only finitely many of these critical temperaments. So there aren't infinitely many you have to worry about. But you can see that what happens at the critical temperament is actually quite complex. So maybe I'll finish by, I think in the interest of time, I'll finish with sort of the main result, which is that the well-tempered, so this is a result from the paper published in 2020, McConnell and MacPherson, is that the well-tempered complex actually is built up from this family, and the well-tempered complex can be used to compute for you the action of a Hecke operator on the cohomology of this space. And you have this analog of, so what you get is this fiber bundle, which is the analog of what you have in the well-rounded retract case, where you just have y and k and you don't have this sort of parameter space I. And it turns out you get a whole continuous family of these retracts, and every fiber deformation retracts onto the well-rounded retract that you have. And so this well-tempered complex is a new object, which I think is of great interest. And let me just finish by saying that these are some papers. There are tons of really fascinating things if people want to talk more about. But these are some specific papers that where a lot of these sort of pictures and ideas come from. And here are the bibliographies. All right, thank you. Any questions?
Yeah, nice talk. Can I ask a question about the picture of the Voronoi decomposition and then the dual thing?
Yeah, here.
So yeah, so I see how the picture on the right is the dual of the picture on the left, but I didn't fully understand why we expect such a relationship between the Voronoi thing, which doesn't seem to have too much relation to the well-rounded retract stuff. So could you say a little bit more about that?
I see. Yeah. So I think that the best way is to come back to this. So the point is that you can describe the symmetric space on the right-hand side as a quotient of this code by homotheties. And on the right-hand side, when you build the well-rounded retract, what you look at is you look at trying to build a spine in this space. On the left-hand side, what you have is you build a series of cells that give you a decomposition. And the point is that essentially the point is that if you take the dual cell complex to the cell complex that you, well, it's not really a cell complex, not exactly the dual, but the point is that where is it? Sorry, there's a slide where oh, here we are. Okay, so the way that you build the Voronoi cones on the left-hand side when you're building this sort of decomposition into open faces is you look at cones on sets of minimal vectors. On the opposite side, when you look at the well-rounded retract picture, you are also looking at minimal vectors. You're looking at lattices whose minimal vectors span the space. So on the one hand side, you are taking minimal vectors and you are looking at the associated lattices. On the other side, you're taking minimal vectors and you're looking at this associated cone. So this is essentially how the duality works.
I see. So as you change the lattice, the inner product that it inherits from the vector space is kind of giving you this phi on the left-hand side. Is that
right? So as you let me see if I can. Right. So the lattice corresponds to when you mod out by k, you get a homothety class of quadratic forms, of positive definite quadratic forms, and the minimal vectors that are associated with this lattice correspond to minimal vectors associated to that quadratic form.
Yeah, okay, I got it. Thanks.
Yeah.
Thank you. Could I ask another question, actually?
Yeah, sure.
So I think you started the talk by saying this well-rounded retract computes the cohomology of these X mod gammas. And it sounds like this well-rounded retract is a really explicit object. But how, like in practice, how possible is it to actually compute the cohomology of this thing?
So yeah, so there are a bunch of different answers to that. One is that there existed before the well-rounded retract some different even more combinatorial techniques for computing cohomology. There's something called modular symbols, which is quite effective. The other answer to that is there is a lot of work that, so if you're very interested in this, what I would do is I would look at, there's a series of papers by Mark McConnell, Avner Ash, Paul Gunnels, and Dan Yazaki, which does computations of cohomology for SL3, and I think also SL4. So there's a lot of work that still has to be done, especially because the original retract that Avner Ash built also works for it works, you know, for number fields and so forth. So number theorists are often very interested in doing those computations as well. The other thing is that, so in many cases it is actually quite effective. The other thing, but there's still a lot of work that has to be done to actually implement it. The other thing to say is that a lot of times what people are interested in is they're interested in either computing the Hecke operator on cohomology, or they're interested in computing some spectral sequences related to sort of the Borel-Serre boundary. And then one has to do a lot more work. So that one has to do, there's a paper by Ash and McConnell that talks about how you extend the well-rounded retract to the Borel-Serre boundary, and then you can start talking about things that are related to automorphic forms and various different sort of cusp classes, which come, cohomology classes, which come from the boundary components. So there, you know, I think depending on what you're interested in computing, it's quite effective, but a lot of work has to be done to actually do the computation. I'm not as familiar with the computer side of things, but there is a huge computer side of things as well. Does that
awesome.
help?
Thank you. Yeah, thank you very much. Nice
Yeah.
talk.
Any other questions?
I have a question about this Voronoi cell decomposition.
Uh-huh.
So this sometimes comes up in, like, when you study moduli spaces of abelian varieties. I mean, you sort of did this, the first example in dimension 1, where you take SL2, you take the upper half plane and you quotient by this SL2Z action. But I think the Voronoi decompositions come up when you try to compactify these spaces, these moduli spaces. Is there a nice way of seeing what, like, I think these compactifications are usually quite singular.
Right.
Sure.
So let's go back to the upper half plane picture. So the Borel-Serre compactification for the upper half plane is you just add this sort of line out at infinity, right? So the unfortunate part about about these pictures. Okay, what I can say is something. Let me start sharing my screen again on the iPad, because I can say something a lot more specific about this in a higher dimensional case. So if you look at, okay, let me do it on this slide since it's blank. So if you look at the case of SP4R, and you want to build a Borel-Serre compactification there, then what you get is, if you look at the way that so let's let X be the symmetric space, and what you want to build is this Borel-Serre compact. Well, first you want to build a bordification of this space X, and then this descends mod gamma. So if you look at the way that the torus in SP4R, so the torus, this is going to be something like T1, T2, T2 inverse, T1 inverse. So this is two-dimensional. It says two real dimensional in SP4R. So it compactifies as something, it compactifies inside this bordification as an octagon like this. And what you get is each of these points, you have vertices, you have faces. You have vertices, you have edges. And each of these vertices corresponds to a parabolic subgroup P. And the same for these edges here, which depend on, I think the inclusion relation goes this way. So you have these parabolic subgroups inside. The way you get this bordification is you look at parabolic subgroups inside your algebraic group, and you basically you slap on points and various higher dimensional cells according to the inclusion relations of your parabolics. So the Voronoi picture, okay, this is SP4R, but you get something similar in SL. The Voronoi picture, if you go back to the upper half plane picture. So what we can do is we have all of these cusp points down here, these rational points, and then we have these open horocyclic neighborhoods of these points that look like this in the upper half plane. And it turns out that the complement of all of these horocyclic neighborhoods gives you, the complement of this gives you this huge sort of central, what's called a central tile. In the upper half plane. And the Voronoi decomposition, I'm not exactly sure there's how the Voronoi decomposition intersects the central tile, but I'm guessing that it gives you some kind of cellular decomposition of the central tile. And the central tile in the SP4 case, for instance, the tile is giving you some information about this interior here. And so you're right that the bordification that you get is quite singular. You have very difficult issues here of, this looks like it intersects like this, but this is you have a hyperbolic metric here, so the geodesics sort of intersect weirdly near the corners. But I think in terms of understanding what the Voronoi decomposition does in relation, I would probably look at this central tile where you have the complement of these neighborhoods of all of your sort of cusp points along here. This is, if you're interested in this, there's a paper by Leslie Saper in the Duke Journal of Mathematics. I can't remember the name of it, but if you just Google central tile, he basically, what he does is he does a Voronoi-esque thing where he tiles symmetric spaces. And so he builds a decomposition not into cones, but into these tiles, which is super interesting and is actually the main tool for understanding how you extend the well-rounded retract from the Borel-Serre boundary. Does that help? I don't know if that was clear.
So on the, yeah, that's great. So on the previous slide, you had these sort of cusp points at those points are sort of distinct for every parabolic subgroup, right? In the compactification.
Right. So these this is a little bit deceptive because you are in the compactification, these actually get crossed by a line, but right, but you don't, right, they're associated to rational parabolics, right? For each rational parabolic, you have an associated point or edge like this.
Yeah, thank you very much.
Yeah, yeah. And then the way that this works is the reason you get some, I mean, I'm very interested in this stuff, but I think it's also sometimes quite confusing. But it's one side of magical thing that in understanding why you get an octagon in the SP4 case is if you look at the sort of the roots for SP4, you have these long roots and these short roots. And this gives you kind of a compass inside the torus, which understands why you get these points. You go out along these roots and you get various different associated parabolics. The roots give you a combinatorial way of describing which flags you take. And the parabolics are the objects that fix those corresponding flags. So that's how you get this association at the boundary. Any other questions? Sorry.
Yeah. Well, thank you so much, Dylan, for the talk and finishing us out strong. for the semester.
Thanks for having me.
Nice talk.